Hello everybody, this video is going to be about how we can predict the products of various types of reactions. So in order to do this, we're going to utilize the fact that these 5 different types of reactions follow some patterns. And if we know the patterns, we can use them to make predictions about what those products might be. May not always work perfectly, right? But remember, at this level of chemistry, we're focusing on learning how these patterns work. So some steps that you're going to need. If I give you the words, you're going to have to turn them into formulas. When we write our formulas, remember, if things are ionic, we need them to be neutral, which means we're going to have to use our crossing over technique to make sure those charges balance out. Another thing you're going to have to be very careful of are diatomic elements. Remember, there are 7 diatomic elements. We have that mnemonic, horses need oats for clear brown eyes, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are always going to end up, as I2 or N2 or H2 when they're by themselves. We're not going to have them as singletons. So you have to know if we say nitrogen, you need it to be N2. You will need to identify the type of reaction so that you can follow those patterns. If you need to use your flow chart to help you do that, great. Eventually, we need to know them well enough that we can do it without a flow chart. We'll need to write our products. If we're writing an ionic compound as a product, we'll need to cross over from scratch. We are not going to be doing what I call stealing subscripts. Every time you write a formula, you take one of each element, you cross over to get brand new subscripts to write a valid formula. Make sure you're also, again, careful of your diatomics. And then once you've written all your formulas, then you go back and you balance it to make sure you have the right number of elements on each side. One thing we have to know is that not all reactions happen in real life. And so there are some charts that you can use to help you predict whether or not a reaction will actually occur. So the 2 charts that we will use are going to be an activity series and a solubility chart. You can find these in the reference section of your notebook, right? So the activity series is going to tell you if a metal can replace a different metal inside a compound. The solubility rules are going to tell you whether something is soluble in water or not. If it's soluble, it can break apart. If it's not soluble, it's going to stay together. So here's a little snippet of that activity series. You can just see the little list over here. Metals can replace other metals if they are above the metal they're trying to replace. So for example, calcium can replace sodium. Sodium can replace magnesium. Magnesium can replace aluminum, etc. Okay? The ones up at the top are going to be more reactive than the ones towards the bottom. If you look here, hydrogen is highlighted. Anything that's above hydrogen can replace it in an acid. So if you have hydrochloric acid, lead can replace that hydrogen, lead chloride. You could get nickel chloride, iron chloride, chromium chloride, etc. But you're not going to be able to have bismuth kick out that hydrogen. Bismuth is just, it's not going to react. So you're not going to get bismuth chloride, right? So you have to kind of use this chart to see whether something is strong enough to replace a hydrogen inside an acid. If you notice, this sodium up here is highlighted. Things above sodium can replace the hydrogen inside a water molecule. Water molecule is pretty strong. It wants to stay together. So there's not very many things that can replace that hydrogen and yank it off of a water molecule, so only sodium and above. We also have an activity series for halogens. Halogens can replace other halogens if they're above that halogen. Remember, up at the top is more reactive. So fluorine can replace chlorine, but bromine, is not going to be able to replace chlorine. So we use this the same way, it's just a much smaller chart. So as an example, if we have sodium chloride and fluorine gas, well, let's take a look. Fluorine is trying to kick out that chlorine and take its spot. Fluorine is stronger, more reactive than chlorine, so fluorine can kick it out and take its place and make sodium fluoride. If we have magnesium chloride with bromine gas, bromine is not above chlorine. Bromine is not more reactive. It cannot kick out that chlorine and replace it. So we say no reaction happens. On a quiz or a test, you'll be given an activity series to use if it matters. If you're not given the activity series, then you can just assume that the reaction takes place. We're not going to make you memorize it. You only have to check and see if you need to follow these rules if you have access to one of the activity series charts. Now for the solubility chart, you can see here it's kind of broken into 3 general categories. If a compound has one of these ions in it, it is always soluble. If there's an alkali metal, it's always soluble. If there's ammonium, it's always soluble. If there's acetate, it's always soluble, etc. Okay? If we have chlorine, bromine, or iodine, it's probably soluble. Lots of them are going to be soluble unless one of these are present. If you have silver chloride or silver bromide or silver iodide, it will be insoluble. Okay, if that silver is there, that is an exception to this soluble rule. Lead chloride, lead bromide, lead iodide, also insoluble. Breaks this solubility rule. It is an exception. Okay, down here, these are going to be insoluble unless you have one of these situations, right? If they're paired with something from up here that's always soluble, that's always going to break the rule down here, okay? The somewhat soluble ones are tricky because that means that they may dissolve a little bit, but you would need so much water that they don't, they don't dissolve that much. So sometimes we'll tell you, like, just assume those do break apart. Just assume they are a little bit soluble enough that you can do the equation. You'll notice over here that we have some little helpful reminders. This AAA is to remind you that alkali metals, ammonium, and acetate are always soluble. CNP, chlorate, nitrate, perchlorate. Some of these, like, people may have an easier time memorizing. If you don't like them, you don't have to use them. I'm never going to give you this column and quiz you on what those things represent. It's just a way to help you memorize these if that's useful to you. If you come up with something even better, let me know. I'll just add it to the files for next year. So a couple of examples that you can write down. Sodium oxide. If I look, sodium up here is always soluble. So sodium oxide is going to be soluble because it has sodium ion in it. Compare that to magnesium hydroxide. If you look down here, we don't see magnesium paired with a hydroxide, but down here you can see here's hydroxide. insoluble except alkali metals and ammonium. Well, magnesium's not either of those, right? Magnesium is not one of these exceptions. So that means that magnesium hydroxide is going to be insoluble. So these are all things that we have to kind of take into account when we start writing out our reactions and predicting our products. So let's do some examples. Sodium plus oxygen yields what? Well, let's write what we know. We know that the formula for sodium is just Na, and we know that oxygen is a diatomic gas, so it's not just going to be O, it's going to be O2. Now I have to ask myself, okay, what type of reaction is that? And when I go through my process of elimination, like it's not combustion, it's not going to be single replacement, it's not going to be double replacement, it's not going to be decomposition, right? It kind of only leaves me with one option, synthesis. So sometimes what people do is they just try to squish it together. Nope, not an option. You cannot do that. The reason you can't do that is this would not be a valid neutral formula. All right, if you had NaO2, this would be an ion. It'd be charged. This is not a neutral formula. This is not going to happen. So what we have to do is we have to cross over from scratch to write a valid formula. We're not going to steal the subscripts and put them over here. So if you look, Na plus O2 minus crosses over to make a nice valid neutral formula of Na2O. So this is correct, except now if you notice, the number of atoms are not balanced on each side, right? So now that I have valid formulas for everything, now that everything is neutral and written correctly, now I'm going to fix the numbers by balancing things. So now I can see that I need 4 sodiums, 1 oxygen, and that will get me 2 of my sodium oxides over here. So what we did is we wrote out what we knew. We were careful about diatomics. We identified what type of reaction it was. We made valid product formulas by crossing over with new subscripts. And then we balanced to fix all the conservation of mass, right? We need to make sure that we have the same number of elements on each side. Let's do another one. Sodium chloride breaks into its components. So the first thing we have to do is write the formula for sodium chloride. Sodium is a +1, chlorine is a -1. I'm going to cross over to get a valid neutral formula, and I get NaCl. Sometimes people will say, wait, isn't it diatomic? Don't you need a 2 here? No, because the chlorine's not by itself. The chlorine is bonded with the sodium, so it's allowed to be a singleton because it's bonded with something else. Okay, so this is totally fine. Well, I told you it's going to break apart, and that's decomposition, isn't it? So then the next thing people do is they break it up like this and they think they're finished. No, 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 there's a big giant problem. Chlorine cannot be by itself. It is diatomic. So I have to write it as a diatomic valid formula. Well, now I don't have the same number of atoms on both sides. So now, in order to fix that, I'm going to balance it. The idea is that you need valid formulas, and then what you can do is change how many of each of those items you have with your balancing. All right, let's do another one. We have aluminum is added to lead 2 nitrate. not nitrite, not nitride, nitrate. Remember, be careful with those polyatomics. Well, aluminum is just a chunk of aluminum, so it'll just be Al. If I have lead +2 and nitrates a -1, when I cross over, I'll need 1 lead and 2 nitrates. So now we have to look, what type of reaction is this? Well, I have an element and a compound. That's going to be a single replacement. Now, because this is a single replacement, I have to check whether or not aluminum is strong enough, reactive enough to kick this lead out and take its place. So we now have to ask ourselves, is aluminum above lead on the activity series? And when I look at my activity series, I see that aluminum is higher on the list than the lead. So it is reactive enough to take its place. The next thing I have to do, because this is a single replacement, is I have to ask myself, is aluminum going to make a cation or an anion? Because that's going to tell me which of these elements it's going to swap with, right? If it's a cation, we replace the cation. If it's an anion, we replace the anion. So aluminum likes to make a cation, so it'll take its place. So instead of aluminum being by itself, we're going to have lead by itself. And we're going to have aluminum combined with nitrate. But this is not a valid neutral formula. I need to cross over. Well, aluminum makes a +3. This is a -1. So I cross over and I get aluminum nitrate comes with 3 nitrates. Now I don't have the same number of things on each side. So now I'm going to go through and I'm going to balance. That feels like a really long problem, doesn't it? Like, oh gosh, I'm so glad we're finished. We got through that whole thing. We had to look at so many pieces and do so many little parts. Unfortunately, I hate to break it to you, you're not finished. Okay, we're not done. We have not thought about the phases. We now need to get out our solubility chart because some of these pieces may not be reacting the way we think they are. And so we need to kind of stop and look at how things are going to react when they're mixed with water, which is what our reactions are taking place in. So get your solubility chart out. Now what we're going to do is we're going to learn how we're going to get all the way down to something called the net ionic equation. The net ionic equation is going to be just the parts of the reaction where things are truly changing, okay? We have our balanced equation. The overall equation, we're going to go through and we're going to add our phases, okay? Aluminum is a chunk of metal, so it's a solid. Nitrate is always soluble, right? So that makes lead to nitrate aqueous. If something's soluble, dissolves in water, we call it aqueous. So we're going to add aqueous to this. Lead is just a chunk of lead. And look, nitrate is aqueous. So I'm going to go through with little subscripts inside parentheses, and I'm going to put my phases. Now what we have to do is write the complete ionic equation. If something is aqueous, that means it's not actually staying bound together like this in my reaction container, in my beaker, or whatever I'm using. When I dump that in with the water, these are going to break away from each other. They're going to be floating around separately. So in my beaker, this is what I end up with. I end up with 2 aluminums. I end up with 3 lead ions floating around. I end up with 6 nitrates floating around. That's going to do some reactions, and we get 3 leads, 2 aluminum ions, and 6 nitrates. And what you should notice right now is that this is showing us that there are 6 items here that don't actually participate in the reaction. Now, if something's not participating, we say it's a spectator, right? If you go to a football game and you're not down there on the field, right? If you're not participating in the game, you are a spectator, right? You're sitting in the stands and you're a spectator. So what we want to do is write the net ionic equation, and this is going to get rid of any spectators. I don't need these. If it's there when I start and it's there when I end, it's not participating. It's useless. The only reason this is here is because the chemical in the stock room came in a jar that was lead nitrate. I didn't have a jar that was lead ions by themselves. I had a jar that was lead nitrate. So that's what I used. But the nitrates themselves are not doing anything. So we don't need to write them on our paper. They are spectator ions. Get rid of them. Now we have the net ionic equation, which is what's actually happening in the beaker. These are the things that are actually having some kind of a change happen to them. If you look, aluminum starts out neutral. Lead starts out as a cation. The aluminum is going to give some of its electrons to the lead, and in the process, the lead becomes neutral and the aluminum becomes an ion. This lead stole the electrons from aluminum, right? Took them. And so that's how it ended up becoming neutral, leaving the aluminum charged. So when I mix these compounds together, this is the actual chemical reaction that's taking place. Thankfully, we don't always have to write the net ionic equation. Most of the time, we can write the balanced equation and be finished. Sometimes I'm going to want you to put the phases so that I can see whether you know how to use your solubility chart. Sometimes I'm going to ask for the ionic equation so that I can see whether or not you understand what aqueous means. Aqueous means they break apart. Can you show me that? And then sometimes we'll ask for the net ionic equation where you're showing us that you understand everything, including the fact that these spectators are not participating. All of that to get to net ionic is one question sometimes. If you don't even know what nitrate is, if you don't even know what NO3 minus is, you're never going to get down here, are you? If you make one tiny mistake of balancing up here, everything else is wrong. This is unfortunately one of those times where it is an all or nothing type of situation. If I ask for you to write a net ionic equation and there's any tiny little piece wrong, it's just wrong. There's no partial credit here. Your net ionic was wrong, right? So you need to be really careful. Please, please, please do not squish your work, okay? Use lots and lots of paper if you need to. I've noticed over, 12, 13 years doing this, the people who tend to make more mistakes are the ones who are squishing their work, writing really tiny, trying to save space. The people who tend to do better are making it very clear, writing one thing on a line, skipping lines, writing big enough so that they don't make small mistakes. And once again, you gotta know your ions. Okay. All right. Let's do number 4. This time we have lead 2 nitrate, and it's going to react with potassium iodide. So I wrote the formulas for you this time. What type of reaction does that look like? We have to know the type so that we know what pattern to follow. double replacement. Good. We have two compounds and they're going to swap, things around. So outsides, insides. That's how I like to think about it. The lead is going to go with the iodide. The potassium's going to go with the nitrate. Remember, you always put cation and then anion. So go outsides and come back insides. And they'll always be written in the correct order. This is not correct because I need to cross over. I am not going to put a 2 down here because I'm not going to steal my subscript. I'm going to cross over from scratch. I take one of each ion. I cross over from scratch. You have to remember that this is lead 2. I figured that out because if nitrate's a -1 and I have 2 of them, lead is going to have to be +2 in order for this to be neutral. So we always assume that the charge, the oxidation state on the metal stays the same unless you're told otherwise. So unless I told you it changed, you just assume it stays. So crossing over, we end up with 2 iodides, and then we just get one of each over here. Now my numbers don't work, so now I have to balance to fix everything. I have 2 iodides, let's put a 2 over here. That's going to give me 2 potassiums, so we'll put a 2 over here. That will also fix the number of nitrates that I have. You have to be able to balance that fast, don't you? Because we're not even close to done, are we? We now have to think about our phases. So you can see why I've been telling you that you got to kind of start knowing these things quickly. We should be able to balance pretty fast in our heads, unless it's a really tricky one, then use paper, right? But hopefully you're getting faster at those skills. Now let's think about our phases. Here's our balanced equation. Now we're going to do our overall equation. So if you use your solubility chart, you're going to notice, hey, nitrate, always soluble. This will be aqueous. Oh, look, we have potassium, alkali metal, always aqueous, always soluble. Over here, darn, lead iodide, that's not aqueous, that's not soluble, that is going to be a solid. Over here, we have an alkali metal and we have nitrate, that's going to be soluble, that will be aqueous. I'm going to pour 2 liquids together and all of a sudden a solid is going to appear. That's called a precipitate. When you suddenly get something that is not soluble, that's insoluble, when you make a solid after mixing aqueous liquids together, right? All of a sudden you get a solid appearing. Now let's write our complete ionic equation. Anything that's aqueous will break apart. Anything that's solid will stay together. Well, I'm going to have 1 lead ion. I'm going to have 2 of these nitrates. I'm going to have 2 potassiums. And I'm going to have 2 iodides. This stays together. Now I'm going to have 2 potassiums over here. And I'm going to have 2 nitrates. So when I'm all finished, it doesn't even fit, right? I had to squish this over here. You can see that everything is broken apart except for my insoluble compound. You should now notice that we have some spectator ions here. Some of these are not participating. If you look, I have 2 nitrates and 2 nitrates. I have 2 potassiums and 2 potassiums. Let's get rid of those. We don't need them. They're doing nothing. They were there before. They're there after. They have not participated. They are spectators. Now I can see that the actual reaction that's taking place is a lead ion is binding together and combining, right, with these 2 iodides to make this precipitate. The only reason the nitrate was here was because the jar I grabbed from the stockroom was lead 2 nitrate. I didn't have lead ions in a jar. I didn't have iodide ions in a jar in my stockroom. I had potassium iodide. So I dumped those in, but this is the only thing that's actually occurring. These nitrates, these potassiums, floating around by themselves. Once again, that was one problem. That's a lot for one problem. You're going to realize that this net ionic topic starts to take all sorts of things we've learned and put them together, and you got to be able to do them quickly. Okay. All right, one last one. Silver nitrate and potassium chloride. What I would like you to do is I would like you to try to predict your products and balance it. Remember, you're going to have to figure out what type of reaction it is. You're going to have to go from the words to the formulas. You'll have to follow your patterns. Okay? Make sure you cross over to get valid formulas, and then you balance it. If you need more time, make sure you pause your video. All right, so silver is a +1 and nitrate is a -1. Potassium is a +1 and chloride is a -1. It's going to be a double replacement, isn't it? I have 2 ionic compounds. That's going to be double replacement. So, outsides, insides. Silver chloride gets made, and then potassium nitrate gets made. Here's the nice thing. It was already neutral, wasn't it? +1, -1, +1, -1. Nice and already neutral. And you lucked out. It's already balanced also, isn't it? So that kind of makes it a little bit nicer, but we're not actually finished, right? We do still need to think about the phases. So we have our balance equation. Now you try to figure out your overall equation. Use your solubility chart and try to see what the phases would be. Is it going to be soluble or insoluble? Is it aqueous or is it a solid? By the way, things are only going to be a pure liquid if you're told. Like water, liquid, right? But it's not very common. Almost everything is going to be a solid or aqueous. So let's use our rules. Nitrate, always soluble, aqueous. Over here, alkali metal, aqueous. Silver chloride. Oh, well, darn. If you look, chlorine is usually soluble, but silver is an exception. So that means this will not be soluble anymore. Over here, we got alkali metal, and we got a nitrate, gonna be soluble, aqueous. The reason a reaction can occur is because we have these ions that are going to be broken away from each other that can then recombine to make new products, right? If you just have 2 solids there, nothing can happen, can it? If you just have 2 chunks of solid, nothing's going to occur. So the phases are important to think about conceptually. Now let's break things apart. We're going to get a silver and a nitrate, a potassium and a chloride. This will stay the same. Over here, we're going to get a potassium and a nitrate. Now you try to find your spectators. You figure out what's just hanging out and not participating. Which ions are not needed in this reaction? Which ones can we do without? Well, we got a nitrate on each side, don't we? And we have a potassium on each side, don't we? So those are not necessary. They're spectators. They are along for the ride, and that is it. So if I look at this, the only thing that's truly happening is that a silver ion and a chloride ion are going to combine to make a neutral, insoluble precipitate. And so, the idea here is that since I don't have a jar of silver ions and I don't have a jar of chloride ions, they had to come with these spectators. That's how I got them to come along, but I don't need them for my full net ionic equation. Net ionic equations are not hard in concept. They are hard. People lose points on them because they are an exercise in being careful. You have to be careful the entire time. It is about the subtleties of knowing your activity series and your solubility chart, your ion charges and formulas, about being able to balance quickly, about knowing how to name things, right? Knowing how to count how many things you have on each side when you're doing your spectators. There's lots of little small places to make mistakes. If you rush, you're probably going to get things wrong. If you're not solid on your foundational, skills like your ions and balancing and things like that, you're probably going to get things wrong. The nice thing about net ionics is that they become very, very repetitive. They become pretty robotic eventually, if and only if you are willing to do enough practice, okay? Some people are going to take to this very quickly and not need a lot of practice. Some people are going to need to spend a lot of time practicing. And that's where you just need to make a grown-up decision about how much effort are you willing to put into the class, right? Based on what outcome you want from the class, okay? The more of these you do, the faster you're going to get. You're going to start realizing, oh, nitrate, done, soluble. Oh, look, there's an alkali metal, done, we're soluble. You're going to get a lot faster, you're going to get more confident, you're going to make fewer mistakes, the more and more you're willing to practice, okay? The last thing I want to show you is something called a particulate diagram. You may have seen these before. I just thought this is a great topic to kind of show them to you in an official way, just in case you haven't. It's just a way for us to help our brains visualize what's happening at a molecular level, since we can't physically see these individual molecules. We can diagram them. We can make a little model of them. So we're going to use little color-coded, or you could label them, circles to represent your particles. One thing that sometimes people get confused about is what counts as a particle. So a particle can be an atom, like a chunk of, iron metal, just Fe. It could be an ion, like a calcium ion, Ca2+. It could be a polyatomic ion, like a nitrate. Or it could be an actual compound or molecule, right? You could have something like O2, or you could have, sodium chloride, right? So you can draw things as little circles. And if it's an ion, you draw a circle by itself. If you're trying to represent a compound, you could draw, two different circles, touching each other. You color code them so you know what you're looking at. Another thing that you need to make sure you do is you use the right number of circles. So if you have a balanced equation and you should have 2 calciums, then you should have 2 circles that represent calcium. So you want to make sure you're using the right number of circles. And then also try to draw them in a way that represents their phases, because that's the topic we're on, is learning about the net ionic, right, and using our solubility charts. So, if it's a solid, draw it clumped together towards the bottom of the beaker. If it's a liquid, kind of spread them out in the middle, right, inside your beaker. If it's a gas, you could indicate that by drawing it, rising up out of the beaker. So your little particle diagram can show you a lot of information, and color coding, labeling, all super important. Clearly these circles are not, to scale, right? Our molecules and ions are not this giant inside a beaker, but we're trying to draw them so that we can see them in our model, in our diagram. So what I'm going to do is go through a couple of the reactions that you saw, that you wrote your your net ionics for, and show you a little particle diagram of them to see if, for some of you that might be really helpful. So this was practice problem number 3. You don't need to recopy the equation. It should already be written down, right? So I'm showing you here that your aluminum came from, a jar, just a chunk of aluminum. And then we had lead nitrate in a jar. We dump them into our beaker, and what we end up having is we end up with lead dumped down at the bottom, right? And you can see our aluminum nitrate was soluble. This was a soluble product. So these end up floating around in my beaker. They've broken apart from each other. And if you look, right, my lead was soluble, or insoluble, I mean. So there were 3 of them, and look down here, there's 3 little leads down here. Now we have 2 aluminum ions, and we have 6 of these nitrates. 1, 2, 3, 4, 5, 6. This was practice problem number 4. We had lead nitrate and potassium iodide. Lead iodide was insoluble, so you can see it down here, right? Chunked down here as a solid. We have the 1 lead ion bound with the 2 iodide ions. And then we end up with 2 potassium ions and 2 nitrates floating around. And here, this was practice problem number 5. We started with silver nitrate and potassium chloride. We dumped them in a beaker. We end up with our silver chloride as an insoluble precipitate down here. And we have a nitrate and a potassium floating around up here. Next, we're going to have silver nitrate and calcium bromide. You try to draw your particle diagram now. You can pause the video if you need a little bit more time. So if we look, our silver bromide is going to be insoluble. It's going to be a precipitate. We're going to have a silver and a bromide bound together, but I'm going to have 2 of these compounds. So down here, here's 1, and here's the second. Calcium nitrate is going to be aqueous. It's going to be soluble. It's going to break apart from each other. So I'll end up with a calcium ion, and I'll end up with my nitrates floating around. All right. So for those of you who are struggling with the soluble-insoluble part, sketching a little particle diagram can be pretty helpful. Sometimes this is a way that we can ask you to show us on a quiz or a test, that you understand whether or not things stay together or break apart, soluble or not. So make sure that even if you're doing pretty good with the soluble-insoluble net ionic thing, that once in a while you practice drawing a particle diagram, just so that you're prepared in case I ever ask you to do that on a quiz or test as a way of showing or explaining your work. All right, everybody, I hope that was helpful. Bye.